This lesson is going to be about rationalizing the denominator. The idea with this is there is this rule in math that we effectively don't ever want to leave radicals in our denominator. Basically, we don't want to have irrational numbers in our denominator. So, kind of the same idea as you would never want to give a final answer of 2/4. Right, 2 over 4. You would never give 2 over 4 as a final answer because we know that we could simplify that down to 1/2. Well, in the same way, when we have 1 over the square root of 2 here, that is not an acceptable way to write an answer. We want to change that. We want to rewrite this fraction in such a way that our denominator is rational again, meaning it's no longer an irrational number like the square root of 2. Well, when we rewrite fractions, really the only way we know how to do that is to multiply our fractions by something in both numerator and denominator, top and bottom, right? We want to multiply by the same thing. The same way if you think about when you used to find common denominators for fractions, when you wanted to find a common denominator, you would find some number that you could multiply by on top and bottom, numerator and denominator, to get both of your fractions to have the same denominator. So we're going to kind of do the same idea here, except our goal isn't to get a common denominator. Our goal is simply to get a rational one. So what we want to ask ourselves is, what could we take the square root of 2 times to get rid of that square root? Right? It's not really the 2 that's a problem, it's the act of it being square rooted that's causing it to be irrational. Well, what's the opposite of square rooting? The opposite of square rooting is to square something. And so what we want to effectively do is we want to square the square root of 2. We want to take it to the second power. Squaring something means taking it times itself. So in that case, it sounds like the way to fix this would be to multiply the square root of 2 times itself. And of course that would mean we have to multiply by the square root of 2 in our numerator as well. Remember, the reason behind that is anything divided by itself is 1, which means if we're multiplying by the square root of 2 over the square root of 2, we're essentially multiplying this problem by 1, and we know anything times 1 is itself, meaning we're not changing the value here. That's the important thing to understand. So if we do this multiplication, in our numerator, 1 times the square root of 2 would be the square root of 2. In our denominator, remember from our earlier video talking about properties of radicals, if we are taking the square root of 2 times the square root of 2, the product property of radicals says that since they are both the same type of root, since they're both square roots, we can multiply them together into one large radical, meaning 2 times 2 would give us the square root of 4. And what is the square root of 4? Well, it is just simply 2. And so this would be the correct way to write 1 over the square root of 2. Understand we did not solve anything here. We didn't find a new number. If you typed 1 divided by the square root of 2 into your calculator, the decimal you would get from that is the exact same decimal you would get if you type in the square root of 2 over 2 into your calculator. Those are equivalent expressions. It is just simply that we prefer this expression of the square root of 2 over 2. That is a more official way, I guess you could say, of writing this. Now let's take a look at this example. We have 1 over 2 plus the square root of 5. Now the problem with this expression is still the exact same problem that we had on the last example. That square root of 5 cannot stay in our denominator. It's unacceptable for us to have that square root of 5 in our denominator. So we want to try and figure out what we could multiply this fraction by in numerator and denominator, same thing on top and bottom. We want to figure out what we could multiply by that would get that square root of 5 out of our denominator. Now the problem is it's not quite as simple as the first example. Because the first example, we just multiplied whatever we had by itself, the square root of 2 times the square root of 2. Well, we can't multiply this one by just the square root of 5. And the reason for that is the 2 that's down there with it. Since this is 2 plus the square root of 5, this would be an expression. The 2 and the square root of 5 are bound together by that addition, which means if I was to multiply by just the square root of 5, while it would cancel out here, I would also have to take the square root of 5 times 2 by distributive property, and that would create a 2 square root of 5. So I would cancel out one square root, or I'd get rid of one square root, only to create another one somewhat by accident. And so because of that, we can't simply multiply by the square root of 5. Instead, what we're going to have to do is use something called conjugates. Now you may recall we have talked about imaginary numbers, and we've done a lesson talking about how to rationalize the denominator with imaginary numbers, and we use the term conjugates there as well. So you may have already be familiar with conjugates. If not, it's not a big deal either way. Basically, the idea is if you have a binomial of, say, a plus b, its conjugate would be a binomial of a minus b. Now it's important you recognize this is not opposites, right? If it was opposites, I would have just called it that. This is something different, that's why we have a different term. Opposite would be going from positive a plus positive b to both a and b being negative. Notice that the a stays exactly the same. The a term is positive in both binomials. It's only one of the terms that is changing, that we're having the opposite of. In this case, it's b. It doesn't matter what the letters are, but b went from positive to negative. Now the reason why we call these conjugates, the reason why these are important, is if you think about foiling out a plus b times a minus b. A times a is a squared. A times negative b would be negative ab, because a positive times a negative is a negative. B times a would be positive ab, because a positive times a positive is a positive. And b times negative b would be negative b squared. If you'll notice, we have two middle terms here that cancel out. Negative ab plus ab, leaving us with just a squared minus b squared. Anytime you take a conjugate times itself, anytime you multiply two conjugates together, those middle two terms are always going to cancel. And so the significance of that is, if we consider that with this problem, if this is 2 plus the square root of 5, meaning think of this as 2 is our a term, square root of 5 is our b term, well then the conjugate would be 2 minus the square root of 5. So if we were to multiply this expression by the conjugate of 2 minus the square root of 5, in numerator and denominator, top and bottom, well, in the numerator there's nothing special going on. 1 times 2 is still just 2, and 1 times negative square root of 5 is still just negative square root of 5. But let's watch what happens in the denominator. Foiling out here, I'm going to erase the a and the b to get out of the way. Foiling out here, 2 times 2 is 4. 2 times the negative square root of 5 would simply be negative 2 square root of 5. The square root of 5, positive square root of 5, times positive 2 would be positive 2 square root of 5. And then finally, the square root of 5 times the negative square root of 5. First off, a positive times a negative is a negative. And by the product property of radicals, like we discussed earlier, 5 times 5 would give us the square root of 25. So if we look at this expression now, what you'll notice is that we have a negative 2 square root of 5 and a positive 2 square root of 5, which means they cancel each other out, leaving us with 2 minus the square root of 5 in our numerator over 4 minus 5, because the square root of 25 is just 5. If you multiply by the conjugate, if you find a conjugate correctly, you're going to be able to get rid of your square root every time. And then simply 4 minus 5 is negative 1. So in some problems, we may stop here if we aren't able to simplify any further. In this case, we can go one step further because we certainly can divide both 2 and negative square root of 5 by negative 1. 2 divided by negative 1 is negative 2, and the negative square root of 5 divided by negative 1 is positive square root of 5. So that would be our final answer for this one. The important thing is that you make sure to find your conjugate correctly. Remember, it is not opposites, it's conjugates. One of the terms needs to stay the same sign. Only one term should flip signs and switch to its opposite. When we had 2 plus the square root of 5, we kept 2 positive. We only changed the square root of 5 to a negative. That's what makes this work out.